Welcome to AI Frontiers, where we explore revolutionary discoveries reshaping artificial intelligence. Today we're diving into 17 groundbreaking papers from July 13, 2025, all focused on computer vision. These aren't just academic exercises, they're the building blocks of tomorrow's autonomous vehicles, surgical robots, and augmented reality systems that will fundamentally change how we interact with technology. Picture this. You're watching a bustling city street from above, and suddenly, every person below becomes translucent, revealing glowing skeletal structures moving in perfect harmony. Their future paths appear as shimmering trails, predicting where each person will step next, how they'll avoid collisions, and when they'll pause to let others pass. This isn't science fiction, it's the cutting-edge reality of computer vision research happening right now in laboratories around the world. What makes computer vision so fascinating is this paradox. Modern systems can process thousands of images per second, detect objects smaller than grains of sand, and track movements with precision that would make a hawk envious. Yet they still struggle with tasks that a 3-year-old finds trivial, like understanding whether a video shows someone actually drinking from a cup or just pretending to. This reveals something profound about the gap between computational power and genuine visual understanding. Think of computer vision as teaching a blind person to see through the most sophisticated technological means imaginable. Just as human vision involves multiple layers of processing, from detecting edges and shapes to recognizing faces and understanding complex scenes, computer vision systems must master increasingly sophisticated levels of visual understanding. But here's where it gets fascinating. These systems aren't just mimicking human vision, they're developing entirely new ways of seeing that sometimes surpass our own capabilities. The field sits at the intersection of mathematics, cognitive science, and engineering, creating this remarkable paradox of superhuman detection capabilities paired with childlike understanding limitations. The first major ecosystem in computer vision research focuses on advanced segmentation and object detection. Imagine trying to separate overlapping shadows on the wall. This is essentially what segmentation algorithms do, but with the added complexity of moving objects, changing lighting, and occlusions. The Memory-Augmented SAM2 work exemplifies this challenge, addressing how surgical robots can maintain precise tracking of instruments even when they temporarily disappear behind tissues or other instruments. Meanwhile, researchers working on infrared imaging are tackling the problem of detecting multiple tiny targets that appear as mixed pixels, like trying to count individual fireflies in a swarm. When your camera can only capture their collective glow, it's like separating individual voices in a crowded room where everyone is talking simultaneously. A second thriving ecosystem centers on multimodal integration, where visual and textual information merge like two rivers joining to form a more powerful current. The Mentor framework demonstrates how machines can generate images from complex multimodal instructions, while VD-Instruct shows how systems can extract key information from visual documents by understanding both what they see and what the text means. This convergence is particularly crucial because human understanding is inherently multimodal. We don't just see objects, we understand their relationships, purposes, and contexts through language and experience. These systems are learning to bridge the gap between what we see and what we understand through language. The third ecosystem focuses on efficiency and optimization, driven by the relentless pressure to make these sophisticated systems practical for real-world deployment. It's like trying to fit the computational power of a supercomputer into a smartphone while maintaining the same performance. QuarterMap introduces post-training token pruning that removes redundant information without sacrificing accuracy, while the dynamic RPCA network revisits classical mathematical approaches with modern deep learning to create more parameter-efficient systems. This work is crucial because it makes advanced computer vision capabilities accessible to applications with limited computational resources, democratizing access to these powerful technologies. The discoveries emerging from this research reveal both remarkable capabilities and surprising limitations. The Memory-Augmented SAM2 breakthrough achieved performance improvements of 4.36% and 6.1% over baseline models on challenging surgical video datasets without adding any parameters or requiring additional training. The Mentor framework reveals that autoregressive models can achieve impressive performance in multimodal image generation, despite using modest computational resources. However, the Glimpse benchmark delivers a sobering reality check, showing that current large vision language models struggle significantly with genuine video understanding, with even the best performing model achieving only 66.43% accuracy, compared to 94.82% human performance. QuarterMap demonstrates that post-training optimization can achieve dramatic efficiency improvements without sacrificing accuracy, removing redundant spatial activations while maintaining or even improving performance. Among all these remarkable contributions, one paper stands out as particularly emblematic of the field's current challenges and future potential. Efficient Multi-Person Motion Prediction by Lightweight Spatial and Temporal Interactions by Yuanhong Zheng and colleagues. This work tackles one of the most fundamental challenges in computer vision, predicting how multiple people will move in three-dimensional space, while addressing the practical constraints that often prevent research breakthroughs from becoming real-world applications. The researchers began with a deceptively simple observation. When you walk through a crowded space, you unconsciously predict where everyone around you will move next, adjusting your path to avoid collisions and coordinating with others. This remarkable ability operates in real time with minimal conscious effort, yet replicating it in artificial systems has proven extraordinarily challenging. The core innovation lies in recognizing that this complex problem can be decomposed into more manageable components through a dual-branch architecture that separates individual and group dynamics. Think of it like an orchestra conductor who must simultaneously track each musician's individual performance while coordinating the overall ensemble. The first branch focuses on individual motion modeling, capturing personal movement patterns and biomechanical constraints that govern how each person moves, learning the periodic nature of walking and smooth transitions between movement phases. The second branch is dedicated to modeling group dynamics and inter-person interactions, taking a global perspective on how spatial relationships between people evolve over time and influence movement decisions. The breakthrough came with the introduction of a cross-level interaction block that integrates information from both branches using attention mechanisms to dynamically weight contributions based on specific scenario characteristics. The system explicitly incorporates spatial distance embeddings, recognizing that physical proximity plays a crucial role in human movement decisions. The implications of this motion prediction work extend far beyond academic achievement. Autonomous vehicles could use these techniques to better predict pedestrian movements, potentially preventing accidents and improving navigation in crowded urban environments. Robotic systems could become more socially aware, moving through human environments with greater consideration for human comfort and safety. Augmented reality applications could provide more realistic virtual characters that move and interact in believable ways. The computational efficiency results demonstrated that the approach requires significantly less computational time and memory compared to existing methods while achieving superior prediction accuracy, making high-quality motion prediction practical for real-time applications through careful architectural design that focuses computational resources on the most important aspects of the prediction problem. Looking toward the horizon, the future of computer vision research appears both challenging and extraordinarily promising. Think of the future of computer vision like the early days of the Internet. We're building the fundamental infrastructure that will enable applications we can barely imagine today. Just as the Internet transformed from a research network into the backbone of modern society, computer vision technologies are evolving from laboratory curiosities into essential components of our technological infrastructure. The convergence of computer vision with other AI fields will likely produce breakthrough applications, with the combination of vision, language understanding, and reasoning capabilities, enabling AI assistants that can truly understand and interact with the visual world. The integration of computer vision with robotics could lead to machines that can work alongside humans in complex environments, with unprecedented capability and safety. Today's journey through the cutting edge of computer vision research reveals a field in dynamic transition, where breakthrough discoveries are reshaping our understanding of what machines can see, understand, and predict. From surgical robots that can track instruments with unprecedented precision to systems that can predict human movement in crowded spaces, these 17 papers represent the collective effort of researchers around the world, pushing the boundaries of artificial intelligence. The recurring themes we've explored, from the quest for human-like understanding to the practical challenges of deployment, reflect a field that's maturing rapidly while confronting increasingly sophisticated challenges. What strikes me most about this research is how it demonstrates the power of interdisciplinary collaboration, with the most significant advances often coming from combining insights from computer science, cognitive psychology, mathematics, and domain-specific expertise. The future holds extraordinary promise for augmenting human capabilities rather than replacing them. This content was synthesized using Claude Sonnet 4 from the 20250514 release, with text-to-speech synthesis powered by DeepGram technology and image generation through OpenAI systems. While human expert review was conducted, oversights may exist, and all original research references are provided for verification. The AI synthesis process involved analyzing the original research papers and transforming complex technical content into accessible explanations while maintaining scientific accuracy. Listeners are encouraged to consult the original papers for complete technical details and to verify any claims made in this presentation. Subscribe for cutting-edge AI research insights with full paper references available on our website. Connect with researchers on social media and explore how these advances impact your field. AI Frontiers serves as your gateway to tomorrow's breakthroughs. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archivepreprinserver.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archivepreprinserver.org.